In our last video, we just kind of gave an overview of the results that we have for unified geometry when we're working with triangles, and now we're going to actually go in and prove a lot of those results, particularly a couple of the ones that have more interesting or more difficult proofs. And to do this, I'm going to make use of Wesley Clark's sketch. We looked at his earlier sketch from that he'd done for his senior project that I directed a few semesters ago and a few years ago, and the first sketch dealt with the basic stuff in hyperbolic geometry, right? Points, lines, angles, and building up the basic tools. And this sketch gives, actually, it says an exploration of hyperbolic geometry, but actually what it really, this particular sketch is really an exploration of triangle properties in geometry where in neutral geometry, where we're going hyperbolic and Euclidean geometry, and we're using the half-plane model for hyperbolic geometry as we've been all semester, and it's doing these geometries side by side. So you want to put his tools sketch that has just the tools in your tools folder, and then you'll have all these tools available. Here's his table of contents. And let's start with congruent triangles. So remember, we talk about congruent triangles. We've already talked about this, so I'm not going to do much work with this except to show you that he has an example of a pair of congruent triangles here on the left that are Euclidean triangles, and then a corresponding setup here on the right where they're a pair of hyperbolic triangles, and he has all of the lengths and angles measured here. And so that these are always set up to be congruent. And notice that we have this side-by-side demonstration with Euclidean demonstrations on the left and hyperbolic on the right. The color coding and the labeling match, so that if we refer to something in one, so if we want to say, for example, that segment AC is congruent to segment FD, that's true over here in the Euclidean drawing, and it's also true over here in the hyperbolic drawing. Somewhere down here there's your edge to the plane for the hyperbolic. Okay, so basically it just goes like that. We have previous and next buttons, we have a table of content button, and so forth. So the next thing we're going to go is to the side angle side condition. Right before side angle side, there's a tab that has some things here. It goes back to the table of contents, but notice that it has a slider exploration, a parameter exploration, and then some constructions, and along the way we'll work on the proofs as well. So the first exploration that we have here for the side angle side condition is sliders. So we can specify a side length here, and notice that changes the Euclidean side length there, AB. This slider right here specifies that angle A. Okay, and it will degenerate to 0 or to pi, but of course we want it to be something in between. And then this will generate the length of that side here. And so notice if we generate a side here, okay, and then go out along the ray this way a certain length, and go out on that ray the same different length here, and by something specified, there's only one triangle, and there's really no way to mess this up. As long as I actually have positive distances here and a proper angle here, there's no way to mess it up. You'll always get exactly one congruence class of triangles. And that's exactly the same as what's happening over here in the hyperbolic illustration, where we see side 1 is the blue side, the angle is next to it, then the angle, and then the side here for the last one. So it's really, let me kind of put them in order, side, angle, and side, like that. And we can investigate this. Now this triangle is staying congruent as I move it around. Now remember how this may be more what you're used to in Euclidean geometry. When you move that around, it looks the same in Euclidean geometry, but these are staying congruent here. So that triangle is congruent to that triangle, congruent to that triangle. Those are all congruent to each other, and the triangle is congruent as I move it around here. So all of those are congruent, and they all have these lengths right here. And here they are measured as the hyperbolic distance, and then the angle measured in radians. Over here we're actually using centimeters. Here we're using, well, the hyperbolic distance there. Now, we can also look here, and this is done by parameters. So let's look over here at the condition on the left. So here you can actually just type in a number that you want, and let's say you can type in 3 centimeters, and then in radians, 0.25 radians, and then let's say 5.1 centimeters, and now we have the triangle constructed. And you could now go and measure the rest of the stuff that's in this triangle now, and then you would find that it's only one thing. So if anybody were to construct this, say on paper, with a compass and a protractor and a ruler, they will get the same measurements. Okay. Now these same parameters adjust here, but because of the scale, we found when we were doing this, if we made measurements here that made a decent looking drawing here, the drawing was way too big over here to fit on our page very well. So what we've done is, if you'll notice, the radian measure of the angle is the same, but what happens here is the S1 you divide by 10 to get the blue length over here as a hyperbolic distance. So if you're trying to get this one to match out a certain distance, you need to multiply the value that you want here by 10, and that's what you need to put in here in S1. Okay? And so there's another exploration there. Now, while we're on the same thing, let me show you one other sketch. Give me a second to pull it up. Actually, I've got it on my desktop. I have made this other sketch called Trigonometry Ultimate. And this is a sketch I use with my trigonometry students. And if you look, it has, look at the table of contents here. Each one of these is a page within this sketch. This is a massive sketch. And this basically goes through every topic in a trigonometry class. So everything that you did in your high school pre-calculus class as far as trigonometry goes, it's covered here pretty much. And one of the things is there's a series of things here, starting with, say, this one here, where we talk about congruent angles. This ought to look familiar because I just copied this and over to one of your sketches. And then this investigates in a similar way to the way Wesley's sketch does here, when it's only Euclidean geometry, but notice that we can specify our angle first, and that generates these two rays and one vertex. Then we can specify a length here. That means it goes out on the green circle length, and it has to be on this red ray here, which means it has to go to point A. And similarly, this one out here specifies side length A, and this gets us exactly one triangle that's there. This one also has the added advantage of, you can also click on that and show all the measurements as well. Also, this one's labeled sort of in a standard order, so that the angles A, B, and C, those uppercase letters are using double duty. They're used to give us the points A, B, and C, but also the angles A, B, and C. More properly, I probably should call them alpha, beta, and gamma, but we're going to avoid that and use capital letters A, B, and C, and hopefully we know from the context whether we're talking about the vertex, the point A, B, and C, or the measure of the angle. Okay? And then lowercase a, lowercase b, and lowercase c then are the lengths of the corresponding sides. Here's a congruent triangle down here that has the same measurements. And of course then we get our conclusion is the side angle side postulate. This one also here is, this one is done by parameter. So I can enter in, say if I want that to be 3 centimeters, this one works with degrees, and say I want 47 degrees for the middle, and then say 5 centimeters. It draws it to scale, and if you click on this, it shows you the additional measurements. This shows you the step-by-step how you would construct a congruent triangle using this. So you'd start by choosing any point C prime, construct an angle, and it goes over how to do that in Sketchpad, but also, of course, you could just use a protractor if you were doing it by hand. Then you go out a certain distance. That's just using your ruler, and this tells how to do it with Sketchpad. Goes out the other side, and then finish up your triangle there. And that triangle, this construction, we don't really have any options along the way, and so this construction generates exactly one triangle. Now, we also have some things called the Law of Cosines and the Law of Sines. Okay, and this goes over proofs of those things, and this is for Euclidean geometry. And so that is what's used to actually find these computations of these sides, and you know how to do this from your trigonometry or pre-calculus classes. But this, notice how this goes through every detail, and again, this is all dynamic. So if I change this to a different number, like say 2, notice it changed all the measurements, all the drawings done to scale, and all the calculations are computed there. And so we've completely solved that triangle, and we can show the area or not there. Okay, and I have basically this set up. I also have of course, there's no proof for the side angle side postulate because it is a postulate. But then for side side side, I have that, and it does have actually go through a proof. Now Wesley's proof, Wesley's sketch, whoops, let's go back to here, is going to be a little better in some sense for us because it also includes hyperbolic illustrations. So there's a few things I put on mine that Wesley didn't have in his, but also Wesley has some things on his that I didn't have in mine. Okay, and then this goes through the derivation of how you construct it. Basically what I had on my other one here, and it goes over how you can go about the construction, and you can go through here step by step, pick a point, specify an angle, use your protractor to measure angle A, and then make a ray, and then rotate to find an angle A prime. Now notice this construction is going on parallel in over here on the left in Euclidean and over on the right in hyperbolic. Everything in this sketch is done in that way, where you have a thing on the left, a thing on the right. One on the left is Euclidean, one on the right is hyperbolic. Then we make our circle of the center of the radius S1, or over here S1 over 10, and we pick where those points meet and then connect up and make our line segment. Now we make a circle of radius S2 on the left, or S2 over 10 on the right, and we get that point where it intersects, connect up that side, and then of course then we connect up the final side, and we have that triangle. Okay, and these triangles right here are congruent by the side angle side postulate. Now, you can just do a Euclidean translation over here, and you see that one lands on top of the other. You can't just cut this out and move it over in hyperbolic, but if you do a translation in the sense that we're just sliding it around here, you see that it does. If you line it up right, it does match up. Okay, so that's how the side angle side situation works. So basically I'm going to come back, and each one of these conditions we're going to come back and do a little video on each one, and we'll use both of these sketches, my trigonometry sketch and the side angle side, or the Wesley's sketch. We'll use both of those in the videos, and of course you have access to both.